There are really three definitions of an acid, but we're only going to use one of them. And the Lewis acid idea isn't written here and isn't used in the test. If you want to be really nerdy, go look up a Lewis acid. But we're going to talk about a Bronsted-Lowry acid and base in all practicality here. And what they mean is that an acid then is an H plus donor. And I know that is kind of the same thing as this, increases H plus molarity in water. But an H plus donor and a base is an H plus acceptor. And that might be OH minus like the Arrhenius version here, where OH is increased and then that could accept the H plus. But it's anything that accepts an H plus would be a base. And something amphoteric or amphiprotic, honestly, I don't know the difference between those uh, terms. Why do we use one and the other? They seem to mean the same thing. Can both donate and accept. So water is amphoteric. It can accept an H or give one. And you might remember from intro class that your classic acid-base reaction gives water and a salt. And so the H would grab the OH and make water, and the B presumably is the positive, and we grab the A minus, and we would get Ba as our salt. And here's an example. Give that a thought. And of course, you got to balance it, which is a bit of a trouble there, but it's possible. Another interesting thing, and this does come up on the test, is ammonia, NH3. And I did my sketch of my Lewis diagram here with ammonia. And NH3 has an unshared pair here. It has an unbonded pair, another cloud, valence cloud there, which means it has another bonding site for something like an H plus. So if we put in something like acetic acid, which is another thing that comes up a lot, they love acetic acid. It's a commonly available weak acid, and in fact, it's the active ingredient in vinegar. So if you give it acetic acid and you put it here with ammonia, the H is liable to come off here, and ammonia does have a bonding site for an H plus here. You could set up a covalent bond. Even though this is donating just a proton and no electrons, this already has 2 electrons to set up a covalent bond with the incoming H plus, and you get NH4 plus. Well, why would it be plus? You said it didn't change the electrons, right? But now the total positive count here is one more than it used to be. This was a neutral, and you gave it a positive H plus, so the total now is H plus 1. This lost its positive H plus, so it's minus 1. Its proton count and electron count was neutral, and it lost a positive, so now it's negative. This one's proton and electron count was neutral, and it gained a positive H plus, so its total charge now is H plus is plus 1. If this is the acid and that's the base, then what we get here is the conjugate base. This is the base that if we gave it an H plus would turn back into the acid. So this is the conjugate base. This is the base that if we gave it an H plus would turn back into the acid. This is the conjugate acid of the ammonia, the original base. This is the acid that if we took an H plus off of it, it would turn back into the base. And those ideas are going to come up. So be familiar with those ideas and terms. Writing the dissociation equation for acetic acid and ammonia. Now, here's another important point. We have acetic acid. By the way, we often cheat with it like this. My college professors got good and sick of it. And I know that AC is what, actinum, I think, on the periodic table. But people get so sick of writing this out that people just cheat. And so this is acetic, and with H in front tells you it's an acid. And you get all the same math answers. So I have been going along with the cheating because I'm sick of writing that too. I just don't bother. I just introduce it right at the beginning. Now, if this was put into water, this has a pretty decent chance of donating an H plus to what? To water. So what really happens, we're going to be a little nerdy here, is that the H plus is donated to water, and we get H3O plus because this was neutral, but it gained an H plus, which means now it's plus 1 overall. This lost its H plus, and it was neutral, so now it's negative overall. And so what you get is hydronium. Hydronium. However, it's also often written as something like this. This is in equilibrium or becomes H plus and AC minus, just because people are a little sick of writing that out. And so we do this, and you know what? You get the same answers. So this is a giant cheat. It's used all the time. We just know that when we say H plus in water, we mean hydronium. In here, water is the acid. How do I know? Well, what is the thing that donated the H plus? This gained one between here and here, so it's the base. Water lost one between here and here, so it's the acid. So water here acted as the base because it gained an H plus. Here it acted as the acid because it lost an H plus. This whole table is complete overreach, and we don't need to memorize weird stuff like this. You do need to find a table of strong acids and bases and know that, though. And then just look what would happen. The H comes off and it's separate. The H comes off and it's separate. Now, this actually could happen 2 more times, but it's unlikely. And that is not one of our strong bases, by the way. This is a strong base, so these come apart. That's what we mean by a strong base, is that when these hit water, boom, it comes apart, and all the OHs separate off all the Ks. And if this separates, because it's a weak base, not all the OHs will come off. When they do, to whatever extent, we'll get one of these and 2 of those. And that kind of thing we need to know. Hydrochloric acid is a strong acid. All the Cl's come off all the H's. And this is not a complete list. Surprisingly, hydrofluoric acid is not a strong acid, and I never quite figured out why to a level where I felt I could stand in front of a class and explain it. But I know that HIClBr are strong acids and HF is not. So don't make that mistake either.